Hello viewers and welcome back to another video on layer 3 of networking playlist. And in today's video we are going to see a basic overview of OSPF protocol. So without wasting much time, let's get started. So the overall OSPF series will contain this content. So first we are going to see an introduction, and then we are going to explore about link state, a little bit of OSPF history, the packet formats which are there for OSPF, then the overview or the working of OSPF, and followed by the demo of OSPF configuration inside CPT, Cisco Packet Tracer, and we are also going to see how we can simulate OSPF inside NS3. So without wasting much time, let's get started with the introduction part. So this video is also an introduction content for the OSPF. So if you're not aware about our earlier videos, or you're the first time on our channel, so I'll suggest you to watch our earlier videos where I have covered RIP and other routing protocols, other layer 3 routing protocols. So yeah, you can watch all those videos. I'll link down all those videos into the description box, or you can also click the I button over here. And now let's start with the introduction part. So in routing itself, we have seen the static routing. Also in the dynamic routing, we have seen inside IGP, distance vector protocol. So we have seen a very brief overview of RIP. We have also seen how we can configure it inside Cisco Packet Tracer. Also we have seen a demo of how we can simulate RIP inside NS3. Now let's look at the another branch which is inside IGP, Interior Gateway Protocol. So other than distance vector, we have something called link state protocols. So OSPF and ISIS are main example of link state protocols. So they are very useful actually in data center networking. So ISIS was the first protocol which was like you can say this was the first routing protocol that was introduced over the internet. And OSPF is also type of a link state routing protocol. So let's learn about OSPF. So in earlier slide we have discussed about link state. So you already know about distance vector. I assume that you are aware about the RIP and working with the distance vector. So link state is nothing but the very similar way of how distance vector works, but there will be some improvements over here. So let's look at those terminologies with link state. So the basics of link state is nothing but a type of algorithm which is used in networking to calculate the best path towards the destination. So in contrast with RIP, what will be different over here is, rather than calculating the hops on the way, we will be calculating the weights of the edges or the links to calculate the best path. So rather than solely depending on the total hop counts which is there in RIP, we are going to see a weight of each and every link that we are going to take towards the destination. And how exactly this is happening? So let's just look at it. So let's say this is your topology where you have 3 devices A, B and C, and this is the configuration, these are the links between them. So between A and C you have 10 Gbps of link, between B and C you have the same configuration, and between A and B you have 100 Mbps link. So now by the looks of it, you can see that 100 Mbps link between A and B will be slower. And let's say there will be a packet coming from A and it wants to go to B. And now let's say the packet takes 2 paths. The first path is this link, 100 Mbps link, the direct connection between A and B. And the next path is the connection between A to C and C to B, which is holding more speed, 10 Gbps and 10 Gbps. Now consider my packet is 1 GB, and let's say the packet goes through the first path, which is direct link towards B. So 100 Mbps, which means the time which the packet will take to travel from A to B, it will be more compared to, let's say the packet will take second path and it will go via A to C and C to B. So the comparative weights of the link which is, let's say for 10 Gbps it will be 1. Let's consider for 10 Gbps link it is 1, and over here also it will be 1 because the same configuration of the link. And let's say for 100 Gbps it will be 10, obviously because the speed is less, so the weight will be more. So the packet will try to reduce the weight that for the path that it took from the source to destination. So link state and distance vector, the main difference between both of the algorithm is, let's say RIP is working between all these routers. So RIP will reduce the hop count and it will configure the link between A to B as best path. It won't look into the link or the speed of the link or the weight of the link. Rather, OSPF, what it will do, in contrast with RIP, it will take this path from A to C and C to B, because it will try to reduce the weight, not only the hop count. So that's the main difference between OSPF and RIP. So again, that's the main difference between link state and distance vector. So let's move forward. So now, as you might all are like aware with the OSPF and link state, these are the main two keywords that you must be aware right now. So let's look at the OSPF history. So the version 1 of OSPF was defined under RFC 1131, and if you currently see this page, it won't be directly visible. The whole RFC is only available in PostScript file, so you can request those files from the owners or the other authors that you have, but this was the file where the version 1 of OSPF was defined. Now the second version of OSPF, which introduced in RFC 1247, as you can see over here, and it's first the IPv4, and it was the first widely used routing protocol for IPv4, as it introduced the very basic concepts of ASPR, ABR, LSAs that we are going to see later on in these slides. So this was the widely adopted protocol. OSPF version 1 was just the overview of OSPF, but this was the main protocol or the main RFC that you must look into it if you want to learn OSPF. Now OSPF version 2 was refined so many times, but this was the most what you can say important refined format for the OSPF version 2, which was defined under RFC 1583, and it has added support for external routing information, which are nothing but type 5 LSAs. Don't worry about this word, we are going to see in detail about this what is type 5 LSAs and everything, but just for now you might want to remember these things. Now also in addition to this, it has added improved intra-area routing and routing table structure. So this was the main improvement for the OSPF version 2. Again, the another important version, the refined version for OSPF version 2 is defined under RFC 2328, and this is the latest, or you can say the most re-drafted format, or you can say most updated version of OSPF version 2. And in this RFC 2328, it suppressed basically the earlier RFCs and added support for stable and well implemented what you can say OSPF. And most of the OSPF protocol that you might see in the vendors like Cisco, Arista, Juniper, they implement this RFC 2328. Now OSPF version 3, which was defined under RFC 5340, and OSPF version 3 has defined the support for IPv6, and some other improvements are also there. So OSPF version 3, which is basically for IPv6, which is defined under RFC 5340. So those were all the important things that you must be aware about with the OSPF history. Now let's look at the packet formats. So why packet formats are really important before actually you start learning the OSPF working or how OSPF works is because OSPF is a protocol, and as you might know, protocol must have some way, some formats to talk with. Basically, let's say there are devices and they want to talk with each other. So there are certain packet formats or the type of, let's say, configuration, or let's say I want to talk with someone, so I must know their language. So the language must contain some letters and some words. So these packets types are nothing but words. The way how OSPF talk with other devices that are also running OSPF. So for that purpose, we must know how OSPF talks. So for that, we must also know what are the way that it can talks. So these are the all the packet types for the OSPF defined under the RFC latest RFCs. So let's look at them one by one. So the first is Hello Packet, which is basically used to discover new neighbors, maintain neighborships and everything. Then we have something called database descriptions, which is used to provide the summary of LSDP, which is link state database. So this is nothing but database which OSPF stores and maintain to have next hop information and calculate the best path. So this is the basically database which it stores. Now the next is link state request, and this packet format we basically request the specific LSA, and LSA is nothing but link state advertisement. So basically, let's say some device has already given some packet, but let's say there is some counter for that entry was expired. So this link state request is used in such scenarios to actually again request the routes. Then we have something called link state update, LSUs. So this packet format are used to send LSAs. So basically, LSAs, multiple LSAs are bundled together inside LSU, and LSU will have multiple LSAs, and LSA is nothing but the entry in database. Now the last packet format, which is link state acknowledgement, which and this packet format is used to send acknowledgement for the LSAs. So if the device is receiving LSUs also, it needs to be acknowledged to the actual sender. So the number of LSAs that it receives here, all those LSAs, the LSAck packet or link state acknowledgement packets are sent to the original sender of this LSU. So these are packet formats for the OSPFs. Let's look at them one by one. So before actually we look into the packet formats, so we just now talk about LSAs. So LSAs is nothing but the information regarding routes, regarding what are the routes that the device has to share. So also there are some subtypes of LSAs. So which means we have seen here that LSUs will bundle some number of LSAs, and each LSA has some different types. So these are the types of LSAs. So let's look at them one by one. So the main types are type 1, 2, 3, 4 and 5. There are other types also like 6, 7, 8, 9, 10 and 11. So which include support for, let's say, IPv6, and there are some other special types of LSAs which we don't need to be aware about those types as this point of time. So let's just look at the basic LSA types. So the first type is router LSA, which is used to advertise the routes within an area, providing information about the routers connected links and neighbors. So in OSPF we define certain areas, so that we will introduce in later slides, but you just remember this, that type 1 is used to share the information within an area. Then we have something called type 2 LSAs, which is also referred as network LSA, which is generated by designated router. So designated router is a special router which is elected in OSPF that also we are going to see in upcoming slide, but just for now you keep this in mind that type 2, which is network LSA, which will be advertised by DR, and it will describe the network topology. So that's the type 2 LSA. Then we have something called type 3 LSA, the summary LSA, and which is used to advertise the which is advertised by area border routers. And area border routers are also special type of routers. They are not elected, but I'll give an information how the ABRs differs from the DR. So just you keep these words in mind. And these LSAs are signed by type 3 LSAs are signed by ABRs, which is used to summarize the network information from other areas. Then we have something called type 4 LSAs, which is ASBR summary LSA, and as the name suggests, it is also advertised by ABR, the area border routers, and it provides the information of autonomous system border routers. So it basically it advertises the information towards the ASP. These are also special type of routers. Again, just remember the words and purpose. We will see the detailed explanation in upcoming slides. Then we have something called type 5 LSAs, which are also referred as external LSAs, which is also advertised by ASBRs, and it contains information about external routes learned from the other routing protocols. So let's say I have two routing protocols running in my device, let's say RIP and OSPF. So the routes learned via RIP, those are advertised through type 5 LSA. So these are the subtypes of LSAs, and these all types of LSAs are included inside link state updates. So now let's look at the packet formats. So when it comes to OSPF protocol, each OSPF protocol will hold this type of packet format: layer 2 header, layer 1 header, layer 1 information, then layer 2 information. On top of that, there will be a network layer information, which is nothing but the IPv4 header, or in case of IPv6, it can be IPv6 header, and then we have OSPF. So over here there will be OSPF header, and we can have any one of the 5 packet types that we have seen earlier. It can be Hello Pkt, it can be LSDB update, it can be LSU, and it can be LS acknowledgement packet. So let's see how it will be. So this is the first packet type that we have seen for the OSPF, which is nothing but OSPF Hello. So this much of part is OSPF header, and this much of fields are defined for the OSPF Hello packet. So let's look at them one by one. So for OSPF header, the first field is version, and version is nothing but, let's say, which OSPF version is running. So for OSPF v2, it will be 2. This all 8 bits defined over here will be 1. Now packet length will be, let's say, the length of the entire packet that is there, just to identify the end of packet. Then we have something called router ID, which is unique for router who send the packet. Basically, there are certain methods to generate router IDs, which we are going to see later on in the upcoming videos. Then we have something called area ID. As I said, OSPF works by as I said earlier, OSPF works by creating area. So the concept of the area we'll see in upcoming slide, but just for now, area ID is nothing but the unique identification to the area, and it also identifies the area from which the packet belongs. And we have something called checksum. So it indicates okay, this information is wrong. The checksum basically is the what you can say error identification method for all those fields. Then we have something called AU type, which is authentication type. So for 0, so for the value 0 over here, it is none authentication, so which means it doesn't require any authentication, as OSPF also supports authentication. So these are the fields. And in, let's say, the AU type is 1, which means simple authentication. So these fields defined over here, which holds the what you can say, the password without encryption for value 1 over here. For value 0, this fields will be zeros or ones, and for 2 value or defined over here in AU type, it will be ciphertext authentication method. So if the AU type is 2, this fields defined for the authentication will hold the cipher of the password, so which means the encrypted password will be stored over here. So these are the types or the fields for the OSPF header. Now we have something called network mask. So network mask is nothing but the mask for the router, the address of the router which is sending this packet. Then we have something called hello interval. So there are certain timers in OSPF. So hello timer is nothing but the interval. So let's say if the hello timer is 60, which means every 60 seconds OSPF hello packet will be sent. This must be same for both of the neighbors, both of the devices, to form neighborship. That also we will going to explore in next slides. Then we have something called router priority, which indicates the priority used for election. So as I said, there will be a certain election for the DR and BDR. So that is designated router and backup designated router. So this priority will indicate the priority for this router to become DR. So if the value is set to 0, router cannot take part in let's say the election of DR or BDR. And we have something called dead interval. So the timer of dead interval will also be defined over here, and dead interval is nothing but the 3 times value of hello interval. Then we have something called designated router, which means the IP address for the designated router. Backup designated router, which means the IP address for the BDR. Then we have something called neighbor. So indicates the neighbor identification by the router ID. So these are the fields for the OSPF Hello packet, and this is the packet format for the Hello OSPF Hello. Now this is the second packet type, which is DB description. So this fields will be same, OSPF header will be same till the authentication part, and we will see what are the fields that are included for the DB description. So the first field is interface MTU, which indicates the maximum length of an IP packet that can be sent by an interface without fragmentation, and which is important for the DB description packet because we might not want the packet to be fragmented when the transmission is happening for this DB description. Then we have some option fields and some flags. So there are I, M and MS flag. These 3 flags are important. So the first flag is I. If the packet is first one in the multiple DD packets, then the I is set to 1. So let's say the database is too large. So the packet sent by devices which might be fragmented at the sender side only. It should not be fragmented when it is in transmission. So it should not be fragmented by intermediate router. That's why we have this interface MTU field. So by default we will choose the lowest MTU and will packet from the sender side only. Will send the packet in such a way that it won't be fragmented in intermediate devices. So let's say if this is the first packet from the sender side, so and there are multiple packets, so this I flag will be set to 1, which will indicate the destination device, the ultimate receiver, that there will be multiple DB description packets coming from the same neighbor. Then we have something called M flag. If the packet is last one in the multiple database description packet, so it will be set to 0. So M flag, which means if the M flag is set to 0, which means I am the last packet. If let's say there are more DB description packet coming, so this flag will be set to 1. So for the first packet, I flag will be 1 and M flag will be 1. And let's say for upcoming packets which are not the last packet, which is not the last packet, So the flag I will be 0 because it's not a first packet, and more flag, or also you can say M flag, will be set to 1 because there are some more packets coming on the way. And if it is last packet, then I, which means initial flag, will be 0, and more, which means M flag, will be set to 0. Then the last flag, which is very important, master slave flag. So this flag will indicate the router ID, that is master or that is slave. So let's say there are two devices exchanging this DB description packet. So there will be one device will be master and one device will be slave. So accordingly, this M and S bit will be set for when this packet will be sent. Now the next field is DD sequence number. So the sequence number of the packet, in order for the ultimate receiver to arrange this packet in order, in case if the packets are not received in order at the receiver side. Then we have something called an LSA header. So it indicates the LSA header carried by the DD packet, which is 20 byte for each one. So this will be header, and next fields that will be over here, which will be the DB description. So all those information will be over here, and this is nothing but the LSA header for the description that we have provided. So this is the packet format for database description. Now we have third packet type, which is link state request. So OSPF header will be constant till the authentication part. So now let's look at the LSR fields. So for the first field, which is LS type, which indicates the type of the LSA, which means what is the type of link state advertisement. So LSA type 1, type 2, all those types that we have seen, that will be defined over here. Link state ID. So it works together with the LS type and advertise the router in the LSA to describe an LSA in routing domain. So which means link state ID is nothing but the interface ID from which the packet is being sent. Then we have something called advertising router, which is the router ID for the router who is sending the packet, and these fields are nothing but the LSAs that we are going to advertise. So this is the nothing but the LSR packet format. Then we have something called LSU, link state update packet format. OSPF header will be same till the authentication. So the first field in LSU is number of LSAs, which indicates the number of LSAs that this LSU packet is carrying. And let's say there are 10 number of LSAs in this LSU packet. So 10 means there will be 10 LSAs over here. And there are 6 type of LSAs that we have seen earlier: type 1, type 2, type 3, type 4, type 5, and type 6. Main types are type 1 to type 5. There are from type 1 to type 11 types of different LSAs that the OSPF will be exchanging. But the main types are router LSA, network LSA, network summary LSA, ASBR summary LSA, AS external LSA, and NSSA LSA. So type 1 to type 6. So this is the packet format for LSU. Now the last packet format for the OSPF, which is link state acknowledgement LSAck. So the OSPF header will be same till the authentication, and the last or the one and only part for the LS acknowledgement packet is LSA header and the LSAs that are being acknowledged. So this indicates the LSA header which is used to acknowledge an LSA. So this is the packet format. So thank you for watching the video till the end, and I hope you are aware about the packet formats, OSPF history, and the basic meaning of link state and everything that we have explained in this video. In next video we are going to see a basic working of OSPF, and lot more things are coming up. We are also going to see an Cisco packet tracer configuration for the OSPF, and we are also going to see an NS3, how we can configure OSPF inside NS3 and simulate it. So that's it for this video now. I hope to see you in the next video. Till then, keep learning and keep exploring.